pristine survey that we've been conducting for the last couple of years, which is focusing particularly on stellar streams and stellar structures in the halo of the Milky Way. And this is work that we've been able to do also thanks to the Gaia survey of the Milky Way sky. And so I'll talk in particular about a result that you might have seen earlier this year. We did a press release in January about this group of stars called C19 that you can see in the bottom left here, which is a stellar stream of an incredibly low metallicity, much lower metallicity than anything else that we know in the universe to date. But before jumping into this particular stellar system, I'd like to talk about the project that we joined with Pristine for this work. And it's work that we started in 2018. It's an algorithm called StreamFinder, whose goal is to find stellar streams in the halo of the Milky Way. And so this is work that was led by Rodrigo Ibata, who's sitting just there in front. And it's, at some level, it's a very dumb idea in the sense that once we have proper motions from Gaia and distances from Gaia, we basically go through all the stars and check all possible orbits for every single star and see whether some of those orbits look like they're populated by more stars than what you expect just randomly from an orbit with that given set of properties. And that's been incredibly computationally intensive once you do that for 1.4 billion stars that are in Gaia, but it's been incredibly rewarding in the sense that we have found dozens of stellar streams, and you have here on the right maps of these different stellar streams in two different distance slices. At the top, it's from 3 to 12 kiloparsecs, and at the bottom is from 12 to 30 kiloparsecs. Some of these stellar streams were known before. The fact that they're so thin on those maps and the fact that they're physically so close to us probably means that a lot of them are produced by globular clusters. In some rare cases, you do see a globular cluster on the same orbit, and you clearly know that these stars were pulled out of that cluster through tidal interactions with the Milky Way. But in a lot of other cases, you basically just see a stream with no progenitor. And so beyond the stem collecting these different objects and just increasing the tally of such streams, they're incredibly useful, first of all, to disentangle the accretion history of the Milky Way halo. What has the Milky Way halo accreted over time? And particularly the stuff that might be different, that might have been different in the past than it is now. The only way to reach these objects is to look in the halo and find these streams. These streams are useful as probes of the dark matter in two different ways. They can be used to constrain the dark matter halo of the Milky Way as a whole and its morphology, but they can, since they're so cold dynamically and thin on the sky, they're also very sensitive to the nearby passage of, for instance, a dark matter halo, subhalo that would be passing nearby. So they can be used as seismographs to try to constrain the number or the power spectrum of dark matter subhalos. But one of the questions we had with StreamFinder is how low significance can we dig? Of course, we will have these, what I'm showing here are the high significance detections, but there will, of course, be lower significance detections. How far down can we trust our data? And what are the properties of those streams if we don't have spectroscopy yet for every single object? And so this is where Pristine comes into play, because we have this photometric survey of the Milky Way. There's mosquitoes now. So as Elsa was just saying, there's more than 6,000 square degrees covered by the Pristine survey that tells us the metallicity of all the stars that were observed down to the depth of Gaia. So for every single stellar stream found in Gaia that overlaps with the Pristine survey, we can get accurate photometric metallicities. And we can, in particular, focus on the streams that are the lowest metallicity ones that are supposed to be the ones formed earlier in the universe. And so we've combined these two surveys to check the reality of the streams, to find new streams, and do a global metallicity survey of all those streams. And that worked better than I expected, to be honest. We have 26 streams in common between StreamFinder and Pristine. You see here on the top, unfortunately, the gray doesn't really work well on the screen. But trust me that in gray behind you have the Pristine footprint of about 6,000 square degrees, and wherever you have a colored point, it is a place, of course, where we have Pristine data. Here, these points are stream stars found by StreamFinder, color-coded by the metallicity, the photometric metallicities found from Pristine. And at the bottom, you see all the different streams. The color here doesn't track anything. It just is a way to isolate the different bits and bobs that we found in the halo. So on top of or including these, in the middle of these 26 streams, we're also able to find 6 new streams because we're able to dig in lower significance maps from Stream Finder because we have the metallicity information added to the information. We're able to find streams that have consistent metallicities, but were maybe a little dodgy if we just use the Stream Finder information alone. And one of the streams that I'll be talking about is a stream called C19 here that comes out as having a metallicity of -3.5, an Fe over H of -3.5 when observed in pristine. So this is a global metallicity of that structure that is less than 1,000th of the iron to hydrogen ratio that you have in the sun. And at the moment, there's no, or before this, there was no structure known with a metallicity below -3. So this is significantly lower metallicity, but it's also generic common for some of the structures that we found. You can see on the right here, the histogram of the metallicity of globular clusters in the Milky Way in black. And you can see that, I mean, if you've been working on that for quite a while, there's more or less a bimodality with things that are quite metal rich, which are some of the clusters that were formed in situ or formed in the bulge. And then you have this extension to metallicities of about -2.4, -2.5 for known globular clusters around the Milky Way. In red, you have the dwarf galaxies that, as you go to fainter and fainter magnitudes, tend to have lower metallicities. And in blue is the metallicity of all the structures that we found. And remember that they're mainly globular cluster streams. And so we're able here to expand the metallicity of former satellites of the Milky Way to a regime that was never probed before, with 3 streams in particular that have a metallicity below -3, Fe over H below -3. And so what we're probing here is most likely the leftovers of now destroyed satellites, probably those accreted earlier, that got time to be destroyed and open a window for us into the earlier formation of satellites that fell into the Milky Way throughout its history. And so just before moving on, you'll notice this one stream, C19, that comes out as having incredibly low metallicity. Of course, we jumped on telescopes as soon as we found it, and we're able to follow up 8 stars with 2 different telescopes, Gemini with Graces, that is, of course, hosted, it's Espadon hosted at CFHT with the optical fiber to Gemini, and then GTC on the Canary Islands with the OSIRIS medium resolution telescopes. And we're able to confirm all 8 stars that we observe. You can see, first of all, that they're all incredibly low metallicity. That's the plot you have on the left here that shows the metallicity for all the stars. And on top of that, you can see, even by eye, that the dispersion metallicity is incredibly low for that structure. So we confirmed the low metallicity, -3.4, and we're able to put a very strong constraint on the metallicity dispersion of the cluster, which is a very strong sign that this is most likely a globular cluster. If you look at at satellites in the halo of the Milky Way, the dwarf galaxies all have a dispersion in metallicity that's quite significant, whereas for the clusters, to first order, it looks like usually like a single burst of star formation at a fixed metallicity. From the Graces spectra at high resolution, we're able to find that there's chemical abundance variations in magnesium and sodium. And again, this is quite typical of what you see in clusters. Once you start looking at the stars in great detail, you see these variations in some of the elements. And so again, the picture provided here is very similar to the picture of a cluster that we know and observe now around the Milky Way. But again, it's significantly lower metallicity than what we know for clusters around the Milky Way. The histogram here is the histogram of globular cluster metallicities around the Milky Way. There was one stellar stream, Phoenix, found a few years ago that was coming out as a metallicity -2.7. And apparently there was just the tip of the iceberg. We do have a population of lower metallicity streams that provide a beautiful window into what has disappeared around the Milky Way as these objects were accreted. If you look at galaxies around, and one of the reasons why this is quite exciting is that already models of globular cluster formation were having difficulties producing objects with metallicity -2.5, -2.7. And if you look at all the galaxies around us, and unfortunately it doesn't come through very well on that screen, every single, on the x-axis is basically different galaxies in local volume, and on the y-axis you have the metallicity of the clusters in those different systems. And what you can see in this, there's almost nothing with a metallicity below -2.5, maybe just a handful of objects. And with something like C19, we're actually pushing significantly lower. And so models of cluster formation and stellar formation will have to be able to explain such low metallicity systems to fit with what we observe in our local surroundings. If you look at models of galaxy formation, usually it's thought that stars with metallicities FE over H less than -3 were formed in the first 1 to 2 gig years of the age of the universe. So again, finding such structures give us a direct window into the formation of very first stars, very first star clusters, very first galaxies. And it's a very complementary view to what we will have in the near future with JWST, that we'll be able to look very far away at these objects as they are forming. We can get a complementary view from around us by looking at what's left of these structures. And in this case, since having just one star here, one star there in the halo of the Milky Way, we have basically the grouping of stars, and we know how they were brought in the Milky Way. We know that they were brought in the Milky Way as a single entity that we should be able to understand and model. One of the interesting consequences of what we were finding in Gaia and Pristine is that if you just sum up the mass of all the stars that are present and correct for all the stars that we don't observe, we expect that there's about at least 10 to the 4 solar masses in that one single cluster. But if a galaxy is too massive, it can't form something of such low metallicity. So you have an upper bound on the mass of a system that can form a cluster like this, and it's about 10 to the 4.5. So it might be that this cluster gobbled up a significant fraction of the gas of the galaxy it formed in very early on, or maybe even all of the mass of all of the gas of that galaxy in a single burst of star formation. Of course, we'll need to get more modeling involved here, and hopefully also to track the stream over larger parts of the sky to really pin down what the mass of that structure was. And that's something that we've started doing in a paper by Jen Yuan, who's a postdoc here. We've been looking for new members further out than where we found the core, the main body of the stellar stream. We're able to find one star. It's that one isolated star you have there in the top right, or on the right side of this plot, which is about 30 to 40 degrees away from where we find the main body of the system. It's a star that has the velocity that's expected from the orbit that we calculated, that has an incredibly low metallicity of -3.4. That's very consistent with what we find in the body of C19, and it's vanishingly, the probability of finding such a star with these properties that would not be linked to C19 is vanishingly small. And so with Jen, we got a few more members, and one thing that's very puzzling is that we find that this stream is at the same time, the chemistry tells us it's most likely a globular cluster, but then the dynamics tell us that it's dynamically hot and quite thick on the sky, and you can see that from the distribution of those stars on the right here. The fact that it's dynamically hot, it gives us more of the picture of a dwarf galaxy being accreted, a dwarf galaxy that is hosted in its own dark matter halo, therefore has a higher velocity dispersion and higher width on the sky. So we have this tension between these two pictures. And Rafael Irani, who's also a postdoc here, has been developing toy models to try to explore whether these properties can be explained if you just disrupt a globular cluster in a Milky Way halo, a static Milky Way halo. And he finds that the cluster, the host, the progenitor, never disrupts effectively. And you do need something of low surface brightness, basically akin to a dwarf galaxy, to be able to explain the observed property of this system. So we have this tension between the chemistry and the dynamics of the system that we need to understand better, but it's certainly quite fascinating. And so to conclude, before Alessandro tells me that I need to conclude, I wanted to, again, like Elsa, point out that the future is bright with the WEAF survey. We're teaming up with the WEAF survey to do the industrial level follow-up of the pristine sources. And it's also useful for this kind of exercises with Streamfinder, because if we have a bunch of stars of incredibly low metallicity and they have a rate of velocity, then we don't have to test for thousands of orbits for every one of those objects to try to see whether there's nearby stars that could be associated to it, because we have the orbit from the Gaia proper motions and distances and the WEAF rate of velocities. So we're gearing up to effectively, as soon as the survey starts, re-explore the halo of the Milky Way, starting from these very low metallicity stars to try to really focus on these low metallicity structures and hopefully find more of these objects like C19 to try to build a statistical sample to explore these early times of star cluster and galaxy formation. And I'll stop here. Thank you very much.
Questions?
Sorry. Wait for the microphone.
Very nice talk, Nicolas. So could you have a use of an 11-meter telescope for improving this kind of study, or 4-meter telescope is enough?
For the photometry, I think 4-meter telescope is enough, because if we're to be able to find these streams, we need Gaia. And so it's fairly bright observations of the sky. And so even though initially Pristine wasn't tailored to Gaia because we started quite a few years earlier, in the end, with 200-second exposures and bad weather time, we're able to reach the Gaia depth. And so these are very well tailored together. Where larger telescopes are useful is actually to do the follow-up, to do the chemistry of these stars, like we did with Gemini and Graces, or GTC and Osiris, is to be able to, once you found interesting objects, try to go and dig in and try to understand what they tell us about star formation, what they tell us about even just their velocity dispersion, right? I mean, some of these stars are magnitude 19, 20. If you want a rate of velocity within a kilometer per second, you need a large telescope.
Thank you.
Hi, thanks for the talk. A question, a curiosity. In terms of dynamical timescale, if it's a globular cluster or a dwarf galaxy, how much would it change? Do you know?
Dynamical timescales as it's being accreted around the Milky Way? Or?
Yeah.
So from the simulations that Raphael Irani did, and these are toy models, right? So don't take it as gospel, but it's quite evident that if it's a cluster on that orbit, on the orbit of that system, it never disrupts. So you need something that's quite fluffy already to be able to disrupt it. I don't have like the orbital time on that orbit is 0.5 gig a year. So that's one of the other things that I don't quite understand. How did this thing survive for so long? Because given that it's such low metallicity, even maybe it was accreted reasonably recently, but where the hell did it come from? Yeah. And if it was accreted early on, which seems more in sync with what we see with the metallicity, and also the fact that it has a Napos center of 30 kiloparsec, and is therefore quite bound to the Milky Way, that hints that it was accreted probably a long time ago. Yeah. How the hell did it survive for so long? Yeah. And so again, I think this requires more modeling, because that close into the Milky Way potential, you have the disk, you have probably giant molecular clouds, a lot of things that might heat it up. And maybe that's why it's observed with such a high velocity dispersion. Yeah. But then there's a fine-tuning issue there, that if it's getting heated up, why hasn't it completely dissolved, right? Yeah. So there is more modeling needed, absolutely, and it's going to be fascinating to do so.
Thank you very much.
Other questions?
So this is from Rafa. I am at the observatory and happy to chat later. But in short, it is hard to constrain accretion time. But with the current short length of the stream, a recent accretion seems likely. That's more of a comment than a question, so I'm not sure if you want to comment on that comment.
No, it's Rafa's work. So,
congrats, Rafa.
So no, talk to him, talk to Rafa, talk to Jen, talk to Anka, talk to Nicolas after his talk. There's quite a few pristine people around.